welcome back. So part C is what we've got left to do. We did A and B. And part C notes that Shepard introduced an additional source of selection in his experiment. He removed 60% of the wild type flies before they could breed in each generation. So now we got to repeat part B, but take some new information into account. The fact that Shepard is exerting artificial selection by going in and taking out 60% of the wild type flies and, I don't know, feeding them to his gecko or whatever it is that you do with excess fruit flies that you don't particularly want. You know, we've had those in our kitchen before, and I wish we could have a gecko, but we've also got a sizable number of cats in the house. So cats and gecko, not a good combination. What's that? Oh, we're back up to 6. Well, at our height, we had 7, and then 2 of them got out, and we've got coyotes out where we live, so I'm afraid we might have lost them that way. And our oldest one finally died of old age. But my wife has taken in 2 new kittens. So I'm just kind of surrounded by cats. It's just this thing that happens. Okay, tomorrow I will include a nice cat picture. But this is the first time in a long time we've intentionally gone out to adopt a cat. I mean, most of the time cats just kind of happen. The one who died most recently, she just kind of showed up on the doorstep one day in our first house, soon that, like a week after we moved in. She just turned up on the doorstep and just meowed at us. It wasn't like, please help me. It was like, hey, open up, I'm your cat. It's like, you know, the decision has already been made and we didn't consult you, but I'm your cat now. So, you know, open up, let's make with the cat food, humans. And that was it. She just kind of showed up and was there. And that's the way most of our cats have been. Either that or 2 of them used to belong to my wife's mother, who lived with us for a while. And when she left us with the cats. So yeah, I have become a cat person, whether I really wanted to or not. So just kind of, like I say, cats just happen. Okay, great. So Shepard's removing 60% of the wild type flies. So let's go back to the whiteboard. And a lot of this is going to come out the same as before. But what I want is, okay, let's do that. We need to rejigger the ways in which we've been calculating fitness. All right, the starting frequencies of the alleles are all going to be the same. That equation in the middle is going to be the same. Okay. All right, if you're a fruit fly and you have the genotype big S, the probability that you're ever going to reproduce is still going to be 0. Okay, that has not changed. If you are a fruit fly with the genotype big S, little s, you know, of all the fruit flies that are born with this genotype, there are going to be some that are not going to reproduce, maybe just because of bad luck, maybe just because of predators, maybe because they're not interested in reproducing, maybe they get a disease. You know, not every fruit fly is going to go off and have kids, but some fraction of the big S, little s fruit flies are going to reproduce, and that fraction, whatever it is, we can call X. Doesn't matter what. the little s fruit flies are the wild type. And we started out assuming that the little s fruit flies had the same probability of reproduction as the big S little s fruit flies. Some of those little s fruit flies are going to succumb to disease or get eaten by a random gecko, or I don't know, move to the big city and become the hottest drag entertainer in town, or something that fruit flies do when they don't reproduce. And we'll start by calling that X. But there is another wrinkle in that these fruit flies are the ones that Shepard is deliberately removing. So if you're a fruit fly and you have that genotype, you have some probability of successfully having babies, right? You have some probability, well, you have some probability of escaping all of the bad stuff that happens to fruit flies, and that's X. You also have only a 0.4 probability of not getting vacuumed out by the experimenter and disposed of, okay? In part C, right, you've got some probability of living long enough to reproduce. But you also have this probability of not getting vacuumed out of the cage by the experimenter. So your probability of successfully having kids, whatever it is only 4/10 as great as the probability of a stubble fly successfully reproducing. Because the stubble flies are not getting taken out by the experimenter and used to feed his gecko, or whatever he does with fruit flies that he doesn't want to keep around. Okay, everybody's seen that. It doesn't really matter what X is. X is the probability that any given fruit fly is going to survive and reproduce successfully. Right? Yes, it's going to survive to puberty, or fruit fly equivalent thereof, and mate. So the probability of a stubble fly reproducing is this mystery probability that we can just call X. The probability of a normal wild type fly reproducing is the probability of that fly surviving all of the natural things that can go wrong, which is X, multiplied by the probability of not getting sucked out of the cage by the experimenter and fed to the gecko. Yes? Remember, the probability of two things is the product of their separate probabilities. So the fitness here is the probability of that fruit fly getting to adulthood and reproducing and not getting killed off by natural causes, multiplied by the probability of that fruit fly not getting sucked out by the experimenter and fed to the gecko. Both of those things have to happen for that fruit fly to reproduce. Yes? So it doesn't matter what X is. What matters is that the fitness of the wild type fruit flies is only 4/10 the size of the fitness of the stubble fruit flies. And then to calculate actual fitness values, we divide each one of these by the highest value, and the highest value here is X, right? 0 is the lowest, and then 4/10 of X is less than X. Yes, all right. So to calculate all of these fitness values properly, we divide 0 by X, which is equal to 0. And we divide X by X, which is equal to 1. And we divide X times 0.4 divided by X, which is 0.4. Yes? Where did I get the 0.4? Because the new information in part C is that the experimenter is removing 60% of the wild type fruit flies before they can breed. That leaves 40% that are left behind. Okay, so we've got three numbers now, and now we've got much greater difference in the outcomes.
Will you ever give us a problem where it gives you one relative fitness and then you use that as your, would that be bigger than another one if you didn't have like an unknown X, but you were given, say, the heterozygous one and it said it was, I guess that, then you would just subtract one?
Okay, run that by me again.
Sorry. Okay, so if you were given one of the relative fitness, they're supposed to equal, they're all supposed to equal one, right?
Well, if the relative fitnesses all equal one, that just means there's no difference in survival and reproductive probability for any of the genotypes, which is another way of saying there's no natural selection happening and we're back in Hardy-Weinberg land.
So you would never just be given straight up, they wouldn't give you homozyte, like they wouldn't just ever just give you straight up one of the relative fitness. You would always have variables.
Yeah, I mean, the variables are my way of trying to make it a little bit more obvious how we actually go about calculating relative fitness. And in practical situations, it can actually be more tricky than this. There's not always a simple way to estimate relative fitness.
I guess I'm just getting confused on where you say like divided by the biggest one. If there's one that's different than X, then how would you know which one's bigger? If there was X, like X was one and then there was another, but it gave you a number.
Okay,
Does
so
that
if you
ever happen?
okay, so if you had no idea what X was, or if X could be greater than one,
Yeah.
okay, it doesn't really matter because as long as you're dividing all three of those fitness values by the largest of the three, then your largest fitness value is always going to be one.
That part, the largest of the three. What if one of the three is not X? Does that ever happen? What if it was a number?
Oh,
They give you a number already.
okay. Yeah, I could.
That
I tell you what, we'll work, once we're done with this, we'll work another problem that goes by a little bit more quickly. And that actually does have some concrete data where you can calculate relative fitness. And I'll show you how that works.
Okay.
So go ahead and hold that thought. Okay, yes.
So you put the point for stubble flies.
Okay, you put the 0.4 with the normal flies. And the reason is that the experimenter is sucking out 60% of the normal flies and removing them from the experiment. And I'm guessing he was feeding them to his pet gecko, but I don't really know. Maybe just flushing them down the toilet or something. Whatever you do with flies you don't want. Anyway, yeah, the experimenter is removing 60% of the normal flies. And that 0.4, that's the probability of not getting removed from the experiment and fed to the gecko.
So it increases. I get what you're saying.
Okay, well, it decreases it. If you're a normal fruit fly, you have some probability of not dying and living long enough to reproduce and having, functional reproductive system. And we call that X. We don't really know what it is. But you also have only a 0.4 probability of not getting sucked out of the experiment. So if you are a normal fruit fly, two things have to happen. You have to reproduce, and you have to not get sucked out of the experiment. And both of those have to happen in order for you to reproduce. And so this X times 0.4 is the probability of both of those things happening.
Would it not go like sinus flies?
Nope.
The little less,
A little less are the wild type normal flies.
big S.
Okay.
Yeah, big S, the ones that are homozygous for the stubble allele, those die. Okay, all right, gotcha. Okay, so we still have this equation over here that still applies. Our first thing to do is calculate W bar. But now we can rejigger this a little bit. So up here, the frequency of big S flies is still going to be P squared. That's 0.07 times 0.07 times the fitness, which is 0. And our frequency in the next generation of heterozygous flies is 2 times 0.07 times 0.93 times 1. And then our frequency of wild type flies in the next generation is 0.93 times 0.93 times 0.4. And that's going to be equal to W bar. So if somebody wants to plug and chug, our new mean fitness is going to be no,
Is that supposed to be like? Is it supposed to be?
no,
It's not supposed to be.
it's not supposed to be.
0.476.
0.476 sounds good to me.
I just got that.
Okay. All right, so whoops. Okay, so we plug all that in, and now our W bar is equal to 0.476. Okay, now what we do is divide every term in that equation by 0.476. And we get this, we get what I've drawn down here. Trying to move things so it's a little more legible. Okay, think this through. We took that equation for W bar and we calculated it to be 0.476. Each of these terms of the equation now tells us how many individuals of each genotype, or what the frequency of individuals of each genotype we would expect to have in the next generation. So the first one here, if there was no selection, then the frequency of homozygous dominant individuals in the population would be P squared, which would be 0.07 times 0.07. So that right there, that would be the frequency of individuals with the big S genotype in a population that didn't have selection. And then this term right there is the frequency of individuals in the population that does have selection. And it happens to be, dang it. Sorry, this is not as intuitive to edit as I'm used to. There we have it. And then that second thing that I've circled right there reflects what the effects of selection are. And so 0.07 times 0.07 times 0 divided by 0.476, well, that's 0, right? So in the next generation, we will not have any big S individuals, which we already knew because that's an embryonic lethal. And individuals with that combination of genes aren't ever born. They die when they're still embryos. Okay, over here, the stuff that I put in yellow. This thing right here, 2 times 0.07 times 0.93, that is 2pq. And that would be the frequency of heterozygotes if we didn't have selection to worry about. If we met all the Hardy-Weinberg criteria, or close enough anyway, that would be what we got. We have 2 times 0.07 times 0.93 would be the frequency of heterozygotes. However, we do have selection, and the fitness of that genotype is 1, divided by the mean fitness is 0.476. So we're taking 1 and we're dividing it by something quite a bit less than 1. In fact, we're taking 1 and dividing it by something that's nearly 0.5. And 1 divided by 1/2 is 2. So this 1 over 0.476 is going to be close to 2. Right? Yes? We already know it's going to be greater than 1. 1 divided by something less than 1 is something greater than 1. In fact, it's going to be close to 2. And what we can already see is that in the next generation, we're going to have nearly twice as many heterozygotes as we would if we did not have any selection going on. In fact, if you want to be specific, what's 2 times 0.07 times 0.93 times 1 divided by 0.476? Anybody want to calculate that? You got 0.27? 274, okay. 27.4% of our flies in the next generation are going to have genotype SS, and they'll be stubbly. Okay, got that? And that's about right. If you recall, before break, we calculated that without selection, about 13% of our flies would be stubbly. Here, with selection, in one generation, the frequency of the stubbled flies goes up to 27%, right? Because we are multiplying this term by something that's roughly 2, 1 divided by 0.476. All right, and then this last one, here again, 0.93 times 0.93, that's q squared. That is what the frequency of homozygous recessive flies with normal bristles would be if there was no selection happening. But in fact, there is selection happening. And we are, whoops, I made an error.
I don't understand what we put it to for that.
Hang on, it's because I made a mistake. Take careful note of it. It's the first time it's ever happened in 23 years of teaching. So funny. Okay. It's because what we want is 0.93 times 0.93, that's q squared. And then we're multiplying it by this number that expresses the effects of selection, and it's 0.4 divided by 0.476. The denominator is greater than the numerator, so that fraction is going to be something less than 1. And what that's telling us is that the frequency of homozygotes is going to be less than it would be if there wasn't any selection. All right. And that should give you approximately what, like 73%, 0.73, I think? 0.729?
777.
0.727, okay. I'll round off, but close enough. And now we have our answer. After one round of selection, 0% of our fruit flies are going to have big S, big S. 27% of our fruit flies are going to have stubble bristles with the genotype big S, little s. And 73% of our fruit flies are going to have normal bristles. And those should all add up to 1, and in fact they do. So now we've got our answer to part C. All right, is this helping at all? Okay, thank you for nodding. I feel a little bit better. Our piece is starting to come together. Yes.
I still feel like there'd be non-zero amount of selection for the chance that it would mate with another heterozygote, and then the further chance that its offspring would be
Okay.
big S.
All right, as long as we have random mating, that's basically baked in. If we had non-random mating where fruit flies were deliberately courting or trying to avoid mates that had normal bristles or stubble bristles or whatever it was, then we'd have to add that, and that would start getting a little gnarly. We'd have to add a repulsion term. But yeah, I promise you the probability of that happening is actually baked into the math. Deriving that would take more time than I feel like I can spend, but I promise you it's there. Can I do number 4? I certainly can. All right, has everybody got this? Everybody got down what's on the whiteboard? Okay, let's go in that case to 4. Which one is 4? Okay, 4 is the one I was going to do already. So let's do 4, and this one should be a bit quicker than the first. So we have a wildflower native to California called the dwarf lupin that normally bears blue flowers, but occasionally wild populations you'll observe pink flowers. Flower color is controlled at a single locus with pink completely recessive to blue. And some poor grad student went around, you think counting clovers for an hour was no fun. Some poor guy must have clambered all around the central coast ranges of California, counting bloody lupins. And in one population of lupins, he found 25 pink flowers and 3,291 blues. Okay. So what would the expected allele and genotype frequencies be if we were in Hardy-Weinberg? Well, okay, help me remember those numbers. We've got 25 pink and 3,291 blue. Let's go to the whiteboard. And I'm going to erase all that. All right. So we have lupins, since blue's dominant and pink is recessive, will represent the blue allele by a capital B and the pink allele by a lowercase b. Doesn't really matter what letters we use, but what the heck. So blue lupins could either be homozygous dominant or heterozygous, right? So your frequency of blue lupins is the frequency of both the homozygous dominant genotype and the heterozygote genotype. And that is, what was that number? 3,270,
And
Nine.
3,091.
200
What's the total population?
is 3,3.
3316, right? 3316. And the frequency of little b lupins, those are the pink, and that happens to be equal to 25 divided by 3,316. Okay, somebody with a handy calculator can plug and chug. Equals 0.992, 0.008. All right, everybody got that? Okay. If we assume we are in Hardy-Weinberg conditions, then what are our allele frequencies? Then the frequency of blue lupins is p squared plus 2pq equals 0.992. And the frequency of pink lupins is q squared, which you already know is equal to 0.008. Now, here's a funny thing. If you wanted to do this the stupid way, you could say, remember that p is 1 minus q and q is 1 minus p, because, right, the sum of both has to equal 1. So we could say p squared plus 2p 1 minus p equals 0.992. Everybody see what I did there? I just substituted 1 minus p to get rid of that q. And I could now turn that into negative p squared plus 2p minus 0.992 equals 0. And that's a quadratic. And I could solve that with the quadratic formula. Remember, what is it? B squared plus or minus the square root of 4a. Yeah. Okay, I always look it up. Yeah, you could solve that with the quadratic formula if you wanted to. You don't want to. Okay. You know, let's not get silly here. Yes.
I guess I'm a little confused. What? Going back to the frequency of the genotypes, we only multiply the total by 2 whenever we're doing 1, right?
No, okay, that multiplication by 2 is when you're calculating frequencies of alleles.
Okay, we're calculating frequency of genotype.
Right. And this is like that Hopi problem, because in this case, we are making the assumption that we're in Hardy-Weinberg. We can't directly calculate allele frequencies because we cannot tell by looking the difference between a homozygous blue lupin and a heterozygous lupin. So out of those 3,291 lupins, some are homozygotes, some are heterozygotes. We don't know how many. So this is a case where we're assuming Hardy-Weinberg and estimating allele frequencies. In the other type of problem, we can directly calculate allele frequencies without assumptions and then test whether the population is in Hardy-Weinberg. Okay, the smart way to do this, of course, is that Q equals the square root of 0.008.
0.0.
Okay, everybody see where I got that?
Kind of combine both ways. I think I answered everything.
Okay,
I started like that, and then I just went to count my Q, and then got my P, then P squared to get my G notes back.
okay. Yeah, I think you did that right. Let's finish working through it. What did we say Q was?
0.089.
0.089? Okay. So P is equal to 1 minus Q, and P is going to be equal to 0.9 911, right?
I did 3 sigma.
Okay, Q is the square root of 0.008, Q is 0.089, right? Okay, and so P must be 1 minus Q, so P in this case is 0.911. All right, and now your estimated frequency of big B individuals is P squared, and that's equal to 0.911 squared. Which equals what? It's going to be like 0.82, I think. 0.83. So an estimated 83% of your lupins are homozygous for the blue allele. And your estimated frequency of heterozygous lupins is equal to 2PQ, and that is equal to 2 times 0.911 times 0.089. Which is going to be roughly 0.18 something. What's that? 0.1?
0.62.
0.162. Okay, so 16% of our lupins are heterozygous, we estimate. 83% are homozygous dominant, we estimate. And that leaves, by the way, 0.008 or 0.8% of our lupins that are pink. That's one we don't have to calculate because we already know it. That the frequency of our pink lupins is 25 out of 3,316. Okay, right, that's the one we don't need a formula for because we're told that. All right? Yeah, we were already told that we had 25 pink lupins out of a population of 3,316. And I hope that guy got his PhD. I mean, you know, tramping all around California counting lupins does not sound like a great deal of fun. I wonder why so many grad students need counseling. Doctor, you got to give me something. I'm having nightmares about getting chased down a dark alley by lupins. Okay, great. Let's go and share this again and see the rest of the problem. Okay, Harding studied the fertility of his lupins by counting the number of seed pods per plant. What he found was that the average number of seed pods on a blue plant was 19.33 on average. But the mean number of seed pods on a pink flower plant was 13.08. For whatever reason, we don't really know what the reason might be. Pink plants produce fewer pods per plant on average than blue flower plants do. Maybe the local pollinators like blue better than pink. Maybe the gene for color is linked to some gene that's got a function in plant reproduction. We don't know. All we know is that the average number of seed pods per plant is smaller for pink on average for pink lupins than for blue. Okay, the stock and easy way to calculate the relative fitness of each genotype is just to divide both of those numbers by the largest one. So the relative fitness of blue lupins would be 19.33 divided by 19.33, which is 1. The relative fitness of our pink lupins would be 13.08 divided by 19.33, which is 0.6 something. 0.677. And we could use those right there. Boom, we've just done part B. We could use those as estimates of relative fitness. Now, this doesn't mean that every one of those seeds is going to germinate. Not every one of those seeds might give rise to a new plant. All it's saying is that the chances of a pink lupin producing viable seeds is only about 67% as good as the chances that a blue lupin will. So again, these are relative probabilities. They're calculated by ratios.
So when I give it a mean number, it's much easier.
Yes. Yeah, the fruit fly problem was a little bit tricky because he's not giving you raw population numbers. He's working with percentages. Here we don't, here we're just given raw numbers. And there's a very intuitive way to calculate fitnesses. You take some measurement of reproductive output, in this case it's seed pod number, and you take those for each genotype and then you divide them all by the highest. It could get more complicated than that. It is possible we could have pink lupins producing fewer seed pods but more seeds per pod. Or we could have blue lupins producing more seed pods, but also more seeds that are infertile because of some sort of left field genetic incompatibility factor. There is no simple formula for calculating fitness. There isn't a formula that I can say, okay, here's this data, take this number and that number and plug them in and boom, you get it. You just have to try to figure out as best you can, what are the numbers that are expressing reproductive success in this problem set. And in this case, the data that we've got is the number of seed pods per plant. So that's what we use to estimate fitness. In the real world, it could turn out that we overlooked something and we have to go back and think about fitness again. You know, as I've said, it's possible we could discover that pink lupins are producing fewer seed pods, but more seeds per pod or something like that. It's possible that blue lupins are producing more seeds, but those seeds have a greater chance of getting eaten by the lupin seed-eating beetle. I don't know if such a thing exists, but it probably does. Maybe the blue lupin seeds are at greater risk for seed predators and the pink lupins are left alone. This could get a lot more complicated, but for the data that we've got estimates of relative fitness that we can use. Woofda. All right. You want to go through one more? Or it's 11:15, we've been going for about 45 minutes here. Do you want to take another break and then pick another one to do?
Do we have to do F1 test?
What's that?
Do you have to calculate F1 test?
Oh, inbreeding?
Yes.
I could work an inbreeding problem for you if you want me to. I'm thinking about leaving that off the test. We're going through this a little bit more slowly than I think I had in mind. And I don't want to hit you too hard with stuff that you may not have completely assimilated yet. Yeah, when we come back, I'll show you how inbreeding works. Well, okay,
Is it not gonna be?
let me rephrase that. Let me rework that there. I'll show you how we can model the effect of inbreeding in population genetics equations. But I will put that on the final, but I probably won't put that on the first exam. You will be responsible for it, but maybe not tomorrow. Maybe. Oh, by the way, I see you've got a copy of the practice exam.
Yes.
The problem with practice exams is that's an old exam from years ago. And I never teach the course quite the same way twice. And I think that practice exam came relatively a little bit later. So in the first question, you've got things like disruptive or stabilizing selection, which we will get to, but it's not something we've talked about yet. I might try to drag that in on Friday.
That's the major.
Okay, so if there's something on the practice exam that looks like it's completely from Venus, that's just material we haven't covered yet, please don't panic. All right, on that note, I will now stop the recording.